So, in our last class we were talking about AC potentiometers. What we have learned in that class mainly is how to use a DC standard cell to calibrate a AC potentiometer, because there is no AC standard cell. That is one important thing we have learned. But then we have ended our class with a question that if the supply to the potentiometer does not have same phase angle with the unknown source, then we cannot get the null at all. So, we cannot use AC potentiometers in that way. Okay. So, in this class, so that means the potentiometer that we have discussed in the previous class, this potentiometer, this will work only if the phase angle of Vs and Vx are same. Okay. So, this potentiometer works only if the phase angle of Vx and Vs and Vx, okay, source supply and unknown are same, else it will not work. So, today we are going to look at two schemes with which we can measure an unknown AC source with arbitrary phase angle. Okay. So, these two solutions, these two potentiometers are called coordinate potentiometer and polar potentiometer. Okay. So, let us first talk about a polar potentiometer. So, in this potentiometer we will need a new instrument, a new equipment, which is called a phase shifter. What is a phase shifter? Let us first understand what a phase shifter is. Okay. So, a phase shifter functionally is a black box which has a input and a output. So, you can give a input voltage V in AC, of course, and so we will get a voltage V out, once again AC, okay, and the frequency of this two will be definitely same. So, whatever frequency you give at the input, output will have same frequency. Okay. So, V out will have same frequency, and we will have like a knob or a dial or something, so which we can turn. Okay. So, this is a control. Okay. So, this you can turn. What happens if we turn it? The phase angle of V out with respect to V in changes. Okay. So, if I drop, say this is time, if this is V in, okay, so this is V in, V out will of course have same frequency, but need not have same phase as V in. So, V out can have a delay like this. So, this is V out, and we can change the position, I mean the phase angle of this V out with respect to V in by moving this knob or dial. So, we can shift this V out maybe here, or towards the left maybe if you want. So, that is also possible. Okay. So, you can shift. So, we can change the phase angle of V out by controlling this knob, changing the dial. Okay. So, we can move this. So, if we move towards the right, maybe it will go, it will have it will have more delay. If we move it towards the left, it may have smaller delay or so. So, this is what a phase shifter does functionally. This is the functionality of a phase shifter, what it does. Now, there are two things that we have to learn. Number one, how a phase shifter is made or what is there inside the phase shifter, and secondly, how to use this phase shifter to measure unknown AC source using potentiometer. So, let us now understand a phase shifter. So, you may have studied this in any other course like electrical machines. Okay. So, but here also we will discuss it, and we will discuss a simplified scheme. Okay. And it is not the actual, I mean the actual device may constructionally a bit different, but the principle is same, theory is same. Okay. So, what we will do, so what we need is 3 coils. We need 3 coils, and the coils are to be placed in a particular manner. Okay. So, let us first assume that there is a plane like this, which is horizontal. So, this is a horizontal plane. Now, imagine another plane which is vertical, okay, which is perpendicular to this. These are some fictitious or imaginary planes. Okay. So, we have 2 planes, one horizontal, one vertical, and now let me place 2 coils, okay, in these 2 planes like this. So, let me draw say one coil with red, which I will put on this vertical plane, like this. So, let me start from here, then let me go like this, then like this, then I'll go like this, and then here, here, here. So this is one complete turn of this coil. Okay, so if you want, we can have more turns. Okay, so now we have two turns. Okay, so this is the start of the coil, and the coil rotates like this in the vertical plane, and then it comes out. Okay, so if I pass any current, it will flow like this. Okay, and if this current, I call this I R for date, is in this direction, then it will create a flux. It will create flux lines which will be in horizontal plane. So the flux due to this will be from left to right like this. Right? Okay, so these are the flux created by this coil. Now let me take another coil which I will put on this horizontal plane like this. So let me start from here and then go round and like this. Okay, so this is one complete turn. Let me have another turn. So I can have many turns like this. And then this is the end of the coil. Okay, so this is the start, this is the end of the coil. Call the current that may flow through this as IB. And if any current flows, then it will create some flux which will be in vertical direction. So the flux due to this will be like this. Okay, so it will be in the vertical direction. Okay, so I may also draw the front view of this arrangement. Okay, another view so that you have a better visualization what I am doing. So the front view. So in the front view, I will see this horizontal plane just like a line. Okay, so this horizontal plane will be seen like a line, and this vertical plane will be seen like a line again. And this blue coil, we will see it like this. Okay, so and these are the turns. Okay, from left to right, these are the turns. Okay, and similarly we have this red one which we will see like this. And the turns or the coil sides are like this. And in the front side we have the current flowing downwards like this. Okay, and this creates flux lines. Red flux lines are in this direction, and blue flux lines are upwards. So they are perpendicular to each other. So they are actually closed curves, but I am not drawing them as close because I do not want to make it clumsy. Okay. Now, if I pass AC currents, say this IR is AC, this IC is IB is also AC, and say these two are at 90-degree phase. Say, let me write that IR is equal to say some I0 cos omega t, and IB is equal to I0 sin omega, or let me write it this way, cos omega t minus 90 degree. Okay, so these are the two currents. They are 90 degree out of phase. If so, then these two flux we can also write them as, say, let me write this this red flux BR. Okay, this will be proportional to IR. So this will be proportional to IR. So let's, and the number of turns of this coil, say, so this will be equal to some B0 times cos omega t, and B this will be proportional to IB. So let me write BB is equal to some B0 times cos omega t minus 90 degree. Okay. And so we are assuming that the number of turns in the red coil is same as the number of turns in the blue coil, then the reluctance for both the coils, etc. Reluctance for both coils same. So under this assumption, if I0 is same as, I mean, if the magnitude of IR and magnitude of IB are same, I0, then this magnitude will also be same. BR and BB will have same magnitude, B0, B0, but they will be out of phase by 90 degree. Okay. So far so good. Now let's see how these two flux lines add up together. Okay. So for that, so let me first draw the two currents. IR and IB. Okay, so I have chosen it to be cos. So this is the origin. And then IB is 90 degree lagging, so we will have the IB here. Okay, and now let us see how these flux lines look like at different time instants. Say at t equals 0. So at t equals 0, then this red current is maximum. So this red flux will be maximum. Okay, so we will have a maximum red flux from left to right. So this is the miniature version of this diagram. Okay, so red flux flows from left to right, and the blue flux is 0 because the blue current is 0. So the blue current is just 0. Now if we add these two fluxes, the resultant will be same as the vector sum of these two fluxes. So the resultant will be same as this one. So this is the resultant. This is from left to right. Okay. So this is at t equals, or this angle at the angle of 0 degree, t equal to 0 degree. So this is 0 degree. Now for let's consider at this point, this is 45 degree. Okay. So at 45 degree, what do we have? This rate flux is positive, rate current is positive, so rate flux will be from left to right, and its value is not as much as before, it's somewhat lower. If it is I0, it will be I0 by root 2, 45 degree. So the rate flux we can draw like this with a smaller length, and the blue flux we can draw like this. It is again upwards, because this current is now positive. Okay, and it is its length is as same as the length of this, their magnitudes are same. So the resultant flux will be this. Okay, so the green is the resultant flux. So this green will be from it's at an angle of 45 degree. This is 45 degree. Okay, because these two are same. So this is at t equals 45 degree. Now similarly, let's consider what happens at t equals 90 degree. Now rate flux is 0, blue flux is maximum and positive. So the resultant will be same as the blue flux, upwards. Okay, so this is at t equals 90 degree. Now similarly, say at here, say this is 135 degree. So what do we have? So we have the rate flux negative, that means now it will be towards the left side, but it's not the peak, it's smaller than the maximum value. Blue is positive, but not the peak. So the resultant will be this. So this angle is 135 degree. So this is at t equals 135 degree. So if you see how the resultant flux looks like as time progresses, you see actually the resultant flux is rotating with the same speed, same angular speed as the angular frequency of these two currents. Okay, and it's rotating. Okay, so we have, so the conclusion is that we have a rotating magnetic field. Okay, so we may also draw the same thing like this. So at t equal to 0, flux lines are from left to right. At t equal to 45, flux lines are like this, resultant flux lines. Then like this, then like this. So the flux lines are rotating. See, this is rotating. Now, so we have created a rotating magnetic field with two coils like this, which are carrying currents 90 degree out of phase, and they are placed in two perpendicular planes. They are spatially also displaced by 90 degree. Now let me take a third coil. Okay, so let me take a third coil which I will put neither on this horizontal plane nor on this vertical plane, but on a third plane, which is say, so let me draw that with a different color. So a third plane, let me draw that here. Okay, so this is at an angle like this. It is neither vertical nor horizontal. This is like this. Okay, and I can, so this will go like this behind, this will also go like this behind, and like, so this is the plane. I am not possibly very good at this drawing. Let me show that here. Okay, so this third plane is like this. In the front view, this is the third plane, and it has another coil. So let me draw that coil with green, which says goes like this. So starting from here, it goes like this, comes like this, and then we can have more turns. Okay, we can have more turns. And this is the out and in and out of this coil. Okay, so the coil is here, this coil is here. From the front view, the coil is here. Okay, now if I put a voltmeter across this coil or an oscilloscope, what do we expect? Will there be any voltage? Yes, of course. Why? Because this coil is here and the magnetic field is rotating. We have a rotating magnetic field. Okay, so the flux linkage of this coil is changing with time. Okay, so the flux linkage of this coil is changing with time, and therefore we will have some, according to Faraday's law, some voltage induced across this. Okay, so let's do some maths if you like. Say if we have the third coil at an angle theta. So this is the third coil. Okay, so let me draw it in the same way as I did before. So Control Z. Yeah, so let me draw it in the same way as I did before. So this is the third coil, okay, which is at an angle, say, theta. Now, how much is the flux linkage of this coil at any particular time? So let's calculate that. So the third coil is here. Okay, so let me take this coil, length of this coil to be much smaller, like this. Okay, I do it on purpose. So this is the third coil. I'll say the cross section area of this coil is A. Okay, so cross section means which area? In this diagram, this area, this area. So that area, or let me just write the area of the coil third coil is equal to A. The third, and it is at an angle of theta. Okay. Now the flux due to the red coil Br, we have written this as some B0 times cos omega t. Okay. So this is the flux from left to right, and how much of this flux goes through this third coil? So that will depend on this projected area, that means this area of the third coil. So the flux due to flux in third coil due to Br, that means red current, is equal to, this will be equal to, if this is theta, if this angle is theta, then this area will be, so this area will be how much? This will be B0 Br times A cos theta. A is the cross sectional area, right? If the angle is theta, okay. So okay, let me measure this angle from here, from this point. Okay, instead of measuring from here, let me measure only from the vertical axis. So this angle is theta. So clearly, if you see that if theta is 0, then projected area is same as A, maximum flux goes. So this is this. Now similarly, we have BB is equal to B0 cos omega t minus 90 degree. So the flux in third coil due to BB is given as flux density multiplied by area in the horizontal direction, horizontal area, okay, multiply. So this will be sin theta. Okay. So the total flux will be in the third coil, I mean, will be this Br A cos theta plus BB A sin theta. Now some simple algebra we can perform. In place of Br, we write B0 cos omega t. So this becomes A B0 cos omega t cos theta, plus here we will have again A B0 cos omega t minus 90 degree multiplied by sin theta. So this you can take common A B0 as common, and we have here cos omega t cos theta plus, now cos this term cos omega t minus 90 is same as cos 90 minus omega t. So this is same as sin omega t sin theta. Please check my calculation. Please check my calculation. If I am doing any mistake, please tell me. Okay. So then this we can write this as A B0. Now cos sin. Okay. So this is same as cos A cos B sin A sin B. So this is cos omega t minus theta. Okay. Cos A cos B plus sin A sin B. So this is how the flux at any instant, this is the flux linkage at any instant in this coil. Okay, so we may need to multiply this with the number of turns of the third coil. So flux linkage will be N, this is the number of turns of the third coil, multiplied by this quantity A B 0 cos omega t minus theta. So this all together I can take it as a constant k, because number of turns is a constant, area constant, B0 is a constant, so we can write this as cos omega t minus theta. And this is a changing quantity. Okay. Now if theta is constant, what is theta? Theta is the position of this coil, and I can keep it constant. I can put this coil at a particular angle. So if we fix theta to some value, then the flux linkage is changing. Okay, then flux linkage is changing with time, and the induced EMF will be equal to rate of change of flux linkage. So the induced EMF E will be equal to ddt of this flux linkage, you call it psi, ddt of psi. So that will be, so k constant, cos derivative of cos is sine, okay, minus sine omega t minus theta multiplied by omega. Okay, and if we keep theta constant, we see E is changing with time. But now we can also change this theta, and therefore the angle of E will also change. Okay, so now if we change theta, the phase angle of E will change. Okay, so for example, let me where is the, yeah, so let me so if this is the timing diagram for the two currents IR and IB in the two primary coils, then the secondary or the third coil, which I am calling the third coil, which you can call the secondary because it's like a secondary coil of a transformer where some EMF is induced. So that E, so this E can change. If I consider, say, theta to be 0, if I keep it at an angle 0, then E will be minus sine omega t. So E will be like this. So this is E for theta equals 0 degree. So that means if I keep this coil here, so I can move this coil. Okay, so this coil is movable. This coil is movable. I can keep this coil here and lock it so that it doesn't move by any chance. I can keep this coil here and lock it so that it doesn't move. So I can change theta. And now if I change theta, so for 0 degree theta, that means when the coil is vertical, you see that this will be the form of the EMF. Okay, and now if I change theta to be something else, so if I take theta to be something like 10 degree or so, then I will have a delay of 10 degree, maybe like this. So this is E for theta equal to maybe 10 degree and so on. So we can change this position of this EMF by changing this position of theta, the angle of the third coil. Therefore, you see that this arrangement is actually a phase shifter. If we give two currents 90 degree out of phase, two supplies in these two coils, then we will get an EMF which we can change its angle by changing the position of this third coil, that means this angle. Okay. So, this is how a phase shifter works. So, in our next class we will start our discussion from this point. We will talk once again about how to use this phase shifter in a AC potentiometer, and then we will talk about another potentiometer, which is coordinate potentiometer, with which also we can measure AC voltage with arbitrary phase. Thank you.